Hi everyone, my name is Gary Patty. I am the CSO of Panone Bio, and I'm here today with ChatGJP. The question is, what is flux analysis and why is it important? Flux analysis represents a different kind of measurement of metabolism compared to the standard readout of label-free metabolomics. Usually when you hear the word metabolomics, what people are referring to is measuring the relative levels or the concentrations of metabolites in a biological sample. Sometimes we also refer to that as measuring the pool sizes of those particular metabolites or lipids. Okay, so that basically just represents how abundant those compounds are in a biological sample. And while abundances, pool sizes, concentrations, levels, whatever word you want to use, while that information can provide a lot of insight into what's going on metabolically, it's often more insightful to try to measure actual biochemical activity, to try to measure the actual rates at which metabolic reactions are happening inside of a biological system. Okay, so one way to think of this metaphorically is that label-free metabolomics, conventional metabolomics, it's taking a snapshot. Okay, it's like standing over a highway and taking a photograph with a camera. Okay, it gives you some sense of the density of cars that are on that street. But from that one picture alone, you can't tell how quickly the cars are moving. Now, you might be able to surmise some information by saying, well, there's a lot of cars in that picture. And so the density of cars maybe indicates that there's a lot of traffic on the street. But you know how fast the cars are going. It could be that the cars are all zipping along at 60 miles an hour, or it could be that there's an accident upstream, up somewhere on the highway, and all the cars are backed up and they're all just sort of sitting there, not moving. Okay, so what we do with flux analysis is the equivalent would be standing over the bridge, instead of taking a photograph, actually taking a movie. Okay, so you're recording the cars as a function of time with a camcorder. Okay, and that obviously now allows you to see how quickly those cars are moving. So how do we actually do that in a biological system? Okay, obviously we can't put a camcorder in there and do it, as I've said, metaphorically. But the way we actually do that is we feed the biological system some sort of stable, isotopically labeled nutrient. It's important to recognize that typically when we do these experiments, we are using stable isotopes. These aren't radioactive isotopes, so the paperwork and the safety isn't as much of a concern as it would be if it was radioactive. These are stable isotopes, so very safe. And you can administer these to cells, you can administer them to model organisms, plants, and even patients. A lot of experiments in where people have administered these to patients. And so these nutrients are labeled with stable isotopes, so these would be things like C13, deuterium, N15. And then these nutrients, as they're transformed, as let's say that you do a C13 glucose experiment, is a very popular flux experiment to do, and you can track those C13 carbons and you can watch how those C13 carbons in glucose get incorporated into downstream products into, say, glycolysis. And if you do that as a function of time, you measure those transformations, where those carbons go as a function of time, you can actually measure the rate at which glycolysis, in this case, is occurring. And you could do that really for any kind of reaction. There are multiple different techniques and computational approaches to do it. And like I said, it's really amenable now to most biological systems. So it provides much more dynamics compared to label-free conventional metabolomics, where you're just getting really a static picture. If you want to take that further and try to get more mechanism and understand more of the dynamics of the biological system, then flux analyses is really a step forward.